Let's go back to horizontal tube again, and we're going to look again at a large section narrowing down into a small section. Again, over here we'll have an area A1 at fluid velocity V1. Over here, area A2, fluid velocity V2. Now, what does Bernoulli's equation tell us? We know over at this end we have P1 plus rho GY1 plus 1/2 rho V1 squared equals P2 plus rho GY2 plus 1/2 rho V2 squared. But if this is horizontal, then we know that Y1 is the same as Y2, and so we can take this term out and this term. And what we have is P1 plus, we can neaten this up a bit, P1 plus 1/2 rho V1 squared equals P2 plus 1/2 rho V2 squared. But we know from the continuity equation that A1 V1 must equal A2 V2. So let's think about this. What does this tell us? If A1 is larger than A2, so if A1 is larger than A2, then we know if A1 is larger than A2, V2 must be larger than V1. And if V2 is larger than V1, then P1 must be larger than P2. So in this situation, the pressure over here must be larger than the pressure in here. The pressure in the larger section of the pipe must be larger than the pressure in the smaller section of the pipe. Now, why is that? That doesn't seem to make sense. You might think, well, it's compressed, and so why doesn't the pressure increase? But if we think about the flow, what's happening to the fluid? If we look at some fluid right in here, the fluid is going from a small velocity to a large velocity, which means we must have more force over here, less force over here. So we must have a greater pressure over here to accelerate that fluid, less pressure over here so that the pressure can accelerate. So the pressure over here, P1, must be larger than the pressure over here, P2. This is called, so what's the bottom line? When a fluid goes from a larger tube to a smaller tube, the pressure decreases. We have a decrease in pressure. This is called the Venturi effect. The Venturi effect. There's a very, very common place to see this that you might have noticed before. Let me change the drawing here and we'll talk about it. This is one of those large, well, this is what's supposed to be, one of those large coffee containers, one of those big coffee containers you might have seen at some kind of reception or something like that, where there's a large storage container for the coffee, and then in the front there's a handle over here. You can pull it, you put your cup under here, you pull the handle over and it fills your coffee up. Something I haven't drawn in, which often these things have, is right here there is a vertical tube that goes up like this. And there's a glass front to it. So you can look inside, let me redraw this. You can look inside. You can look inside the tube and see the level of the coffee inside. So by looking at the glass front of the tube, you can see what the level of the coffee is. Now, this is the interesting part. You put your cup under here, you open up the valve, and the coffee starts coming out. So now we've got a large tube going into a small tube, coming out of it, a small opening over here. What happens to this level of coffee? Well, you think, well, it's going to go down as it empties out. But something very interesting happens. As soon as you open this up and the coffee starts coming out, this level drops way down. And then when you close it off, the level goes back up to wherever the new level of the interior coffee is. Why does it drop down? And next time you see one of these coffee things, even if you don't drink coffee, go have a little bit of it. just to try it, to notice this, or at least watch someone getting some coffee. When you open this up, this is going to drop down because what happens to the pressure here? The pressure here decreases. When we have flow here, and we've got a low velocity, high velocity, large opening, small opening, we're going to have a decrease in pressure. The pressure at this opening here drops down. But as soon as we stop the flow, when there's no more flow and the velocity goes, all velocities go to zero, the pressures go back to the same value, and this will go back up. It's a very, very interesting, very, very simple example of the Venturi effect. So next time you see one of these big coffee things, take a look at it and see if you notice that. So Bernoulli's equation can show us some very, very interesting behaviors in fluid flow, but there are some problems with it. And the problems come about because of the two assumptions of the approximations that we made. Remember, what were they? First, that the fluid was incompressible. Well, that is definitely not going to be true when we have gases flowing. So if we're looking at airflow, air is definitely not incompressible. Also, we assumed no energy loss, in other words, no viscosity. But obviously, fluids typically do have at least some viscosity. Some fluids have a lot of viscosity, and so the more viscosity that it has, the more compressible the fluid has, the more compressible the fluid is, the less accurate Bernoulli's equation will be. But it can still give us some very, very good qualitative results for different behaviors. Well, let's take a look at what happens when we do take into account viscosity or changes in density, the compressibility of the fluid. First, viscosity. So what causes viscosity? Let's imagine that we've got a fluid flowing through a container here. So here's a pipe or a tube. So we're not even going to change the size of the tube, just a constant tube. From adhesive forces. Remember, adhesive forces are forces between different kinds of atoms or molecules. The atoms and molecules in the fluid are going to be attracted to the atoms and molecules in the, I'll do the other ones in a different color, the atoms and molecules of the walls of the container. So that's going to tend to slow down the motion of the atoms and molecules of the fluid near the wall. So down here and then up at the top surface, we're going to have some forces of attraction between the fluid particles up here and the walls. That's going to slow down these. And then the cohesive forces between these particles and molecules, atoms and molecules that have slowed down are going to slow down the ones next to them. That's going to have an effect on the fluid that is close to them, which will have an effect on the fluid close to that, etc., etc. So what effect does that have on the flow rate, the velocity of the fluid? Well, what happens is basically near the walls we end up with very, very small velocities, maybe even zero. And those velocities increase then as we get towards the center and then decrease again as we get towards the other side. So one approximation that is sometimes made is that we assume that this shape from the wall to the center, looking at it sideways, is a parabola, but in 3 dimensions. It's not just a single line, but in 3 dimensions, imagine like a rounded cone shape called a paraboloid. So often an approximation used for the velocity in a tube is a paraboloid. Fastest in the center, highest velocity in the center, and then decreasing to 0 at the very edges of the container. Okay, very good. That is then where the viscosity is coming from for the fluid. And then we also have, because of the viscosity, internal forces of the fluid are going to decrease the pressure as we move along the fluid flow. So because of these forces, the pressure over here is going to be higher than the pressure over here, because this the forces over here have to overcome these viscous forces of the fluid itself, then decreasing as we move along with the fluid. So the pressure itself, even without changing the size of the container, the height of the container, anything like that, pressure will decrease with as we move along in the direction of the fluid flow. Okay. What we find is that the change in pressure, the drop in the pressure, is typically proportional to the flow rate. How much fluid is actually flowing through the tube. Just imagine, if we have a very slow or small flow rate, then the change in the velocity across here is not that much, because we're not going from very large velocities to much smaller velocities. While if we have a very large or high flow rate, then the velocities in the center are going to be considerably different than the velocities closer to the sides. So the change in the pressure is going to be much more when we have higher flow rates than smaller flow rates. What we can write then is that the change in the pressure is equal to P1 minus P2, in other words, the initial pressure minus the final pressure, the change in the pressure, is equal to the flow rate, I sub V, this is the flow rate, times R, where R is called the resistance to flow. The resistance to flow. Now, R will depend on the distance that we're considering. Over what distance of the pipe are we looking at? The larger the distance, the greater the change in the pressure. So we expect R to depend on the distance. We expect it to depend on the radius of the pipe. The larger the pipe, we expect the fluid to be able to flow more easily than through a smaller pipe. So we expect R to depend on the radius of the pipe. And then also the viscosity. Whoops, viscosity I think actually is with an S, viscosity. The more viscosity we have, the greater the resistance. Let's take a look at viscosity. How do we go about measuring viscosity?